Hey everybody, welcome to our next YouTube video all about chemical reactions in Unit 4. Now, this particular video covers quite a few topics in Unit 4. So there is a whole section just on representation of reactions, which you've been doing in Chem 1 and Chem 2 and throughout AP Chemistry. There's also a section on physical and chemical changes, which you did way back in Chem 1. And we also talked about the 5 very basic types of reactions. So this particular video covers a very wide range of Unit 4, which why I think we're going to get through Unit 4 pretty fast. So this is just a nice review of what you did in Chem 1 with me, with Dr. Clark, or with Mrs. Bartholomew. Regarding reactions and with physical and chemical changes. So here is an example of a chemical reaction. More specifically, this would be called a single replacement or a redox reaction, which is what we use in solution chemistry. In this case, we are reacting solid magnesium with aqueous hydrochloric acid, which means it's dissolved in water, to produce hydrogen gas and magnesium chloride, which is also dissolved in the water. You did this back in that standard molar volume of a gas lab. So this is one type of chemical change that you might see in a lab. And a chemical change is the same thing as a chemical reaction. But a lot of times those words are interchangeable. Normally chemists will use the word reaction instead. And that's when you have a transformation into a totally new substance. So in this case, you reacted the magnesium metal and we produced magnesium chloride, which happens to dissolve in the solution when this reaction is over. So you're producing something that wasn't originally there before, and that involves breaking of bonds and forming new bonds. So in this case, you did have to break some of the metallic bonds in solid magnesium. And that solid magnesium ends up forming an ionic bond with chloride ions from the hydrochloric acid. So chemical changes always involve a transformation of a new substance, and usually that's done by breaking and forming new bonds. Here's a great example of a chemical change, not just that example at the top, but anytime you have in the evolution of heat or light, that's typically a chemical change or a chemical reaction that's occurring. And here are some other examples that tell you if a chemical change or a reaction has occurred. So the production of heat or light, the formation of a gas. So that's why in that standard molar volume of a gas lab, which is what this represents, is a chemical change because you produced a gas that wasn't there previously. Formation of a precipitate, which of course is a solid material, and a color change. On the other hand, chemists can also see something like this. So this also represents a reaction of sorts, but in this case, this is not a chemical reaction. What happens here instead is you have water, liquid water, that's transforming into gaseous water. This is not a chemical change, and that's because you're not breaking any intramolecular bonds within those water molecules. You're not breaking covalent bonds, but instead you are breaking intermolecular forces. So physical changes the properties of the material, but not its composition. All that's changing when I vaporize water is the amount of energy the particles have. Liquids have that vibrational and translational energy, whereas gases gain that rotational energy. So all you changed was the properties in that aspect. It's still H2O bonded to one another. You're not breaking any chemical bonds. And that's what this next part here says. Typically involves breaking of intermolecular forces. So hydrogen bonds do need to be broken in order for liquid water to go to a gas. And that's because the gas particles have to spread out much farther. Therefore, hydrogen bonds do need to be broken for that to happen. So here's an example of water getting warmer and thus reaching its boiling point. This is water down here, H2O, and this is also H2O. All that's changing is the amount of energy the particles have, thus hydrogen bonds are breaking, which is making the water molecules space out farther from one another. So some examples you might see of physical changes, changes of state. Anything that's a change of state is always a physical change. Again, because the energy of the particles is the only thing that's changing, not the chemical composition. And also forming and separating mixtures could also be physical changes. But this is an interesting one because in the chemistry community, there is a little bit of kind of arguments about this. Is a solution, making a solution, a physical change, or is it a chemical change? So here it is. I have salt, I dissolve it in water. You've seen something like this before. Here's your salt crystal, here's your polar water molecules. The positive sides of water are attracting the anions, and the negative sides of water are attracting the cations. So this picture is not great because normally they would show these green atoms either of different sizes or different colors, but whatever, this is just the one that I could find. Usually with physical changes, like we said before, there's no bonds that are being broken. But technically, when you are dissolving a solute in a solvent, you are breaking some type of bonds. In fact, you're breaking the ionic bonds within the structure here, the ionic structure, and you're breaking hydrogen bonds, which are holding water together, and you're forming those ion dipole intermolecular forces of attraction. So dissolving water or dissolving salt in water is often categorized as a physical change. That's normally how I would categorize it because it's still salt water. They still retain their properties. You can still separate those two via evaporation and have the salt and the water. However, some other chemists would argue that this is in fact a chemical change because, like we said, you have ionic bonds being broken, and the hydrogen bonds are also being broken, and then you're forming those ion dipole intermolecular forces. So therefore, others would categorize this as chemical, which I always think is like kind of like, how could it be both? But I guess it just depends on how you look at it. Another thing that's interesting about dissolving certain solutes in solvents is that they could either absorb energy from the environment or they can release energy. And that's another piece of evidence that chemists use to determine if a chemical change has happened. Was there heat or energy that evolved off of that? And because sometimes heat is given off or it's absorbed, when it's absorbed, it feels really cold actually. That's another piece of evidence that a chemical change has occurred. So it's really interesting. And again, it just depends on how you look at it. So I just figured I would show that to you as well. And of course, there are the 5 different types of chemical reactions. I'm not going to spend a lot of time on this because you've all seen this before. So of course, you can always determine if a reaction has happened by looking for those chemical changes. The first type of reaction is a synthesis reaction. So if you're synthesizing something, that normally means you're putting it together. And that's exactly what a synthesis reaction is. You have 2 or more substances that are combining to form one totally new compound. For example, if I have the elements A plus X, you're yielding AX as a new final product. So you have 2 reactants forming one final product. So some examples. We have magnesium reacting with oxygen to produce magnesium oxide. 2 more simple elements become something more complex. Here's another example with sodium and chlorine. And here's another example of calcium oxide and water. There are 2 examples in which you would have 2 smaller compounds come together to produce a more complex compound. And of course, synthesis reactions are not just for elements, but most of the time, and for our sake, we normally just look at them in terms of elements. They're much easier that way, but you might also sometimes see these 2 very small molecules. And there are some steps to predict the products for a synthesis reaction. Basically, what you need to do is identify the charge when each reactant element forms an ion. Then the cation is always written first in your formula. We've talked about that. The cation is the positively charged ion. You'll switch your charges so you correctly write the formula for the new product. And then, of course, you want to balance that equation. Always double check to make sure it's balanced. So element plus element gives you a compound. And those two instances in which compounds become more complex compounds, we have metal oxides in this case. That's normally what you have to keep an eye out for. So a metal oxide plus water gives you a metal hydroxide, where a hydroxide is that OH minus 1 group. Whereas if you have a metal oxide reacting with carbon dioxide, you will form a metal carbonate. And of course, the metal varies. It just depends what metal is in the oxide, of course. Those are all examples of synthesis reactions. Primarily, it's when two elements combine to form a compound. The next is a decomposition reaction, which is the opposite of a synthesis reaction. This is when a single compound is breaking down into two or more simpler substances. The exact opposite of synthesis. AX yields A plus X. The only thing is, these types of reactions normally don't happen on their own. These generally need some sort of energy that's applied to them, some sort of heat, some sort of energy, some sort of electric current needs to occur with these as well. So they're not going to be spontaneous. You do have to force compounds to decompose in one of those few ways that I just mentioned. So some examples. You have water. You can break water up into hydrogen and oxygen. I showed you that demonstration that I showed my Chem 1 class. So if you introduce an electric current to water, you can break it up into its component elements. Just make sure you always check for those diatomics. Hydrogen and oxygen are both diatomic molecules. Diphosphorus trioxide breaks up into its elements. Phosphorus is one of those ones that comes in fours. So that does break up into P4 plus 3 diatomic oxygen molecules. And you could also look for those carbonates and hydroxides with decompositions as well. So calcium carbonates, or metal carbonates, I should say, will decompose into a metal oxide and carbon dioxide. So here's your metal oxide, which is just a metal bonded to oxygen, and carbon dioxide right here. These ones I think are actually a little bit easier to do than synthesis reactions. So basically, when you have your one reactant, you're going to separate the elements that comprise that compound in your product side. Look for diatomic molecules and add a subscript of 2 as necessary so that your Bofinch, bromine, oxygen, fluorine, iodine, nitrogen, chlorine, and hydrogen. Remember, phosphorus comes in 4s and sulfur comes in the tribes. Sulfur comes as an 8, so S8. And lastly, you need to balance that. Pretty simple. And sometimes, like I said, you might have those compounds decomposing into more simple compounds. You want to look for those metal hydroxides and those metal carbonates. And there are your products for each of those examples. Basically, it's going to be a metal oxide and then either water or carbon dioxide. It just depends which of those compounds you're starting off with. The next reaction is a single replacement reaction. And this is when you have an element that's replacing a similar element in a compound. When we say similar, normally you're switching cation for cation, or you're switching anion for anion. So positive for positive or negative for negative, which is what these general equations are showing. Here, we can assume that A and B are similar because they are both at the beginning of the alphabet. Therefore, they are switching places. B isolates itself out and A bonds to X. Or you can have Y combining with BX, or not combining, reacting with BX. You can assume X and Y are similar because they are both at the end of the alphabet. and therefore X would isolate and you would form By from that. And some examples. Magnesium, here it is again. So magnesium and hydrochloric acid gives you hydrogen gas and magnesium chloride. Here, magnesium and hydrogen are switching places, and that's because both of those are positively charged. Notice we did include the subscript of 2 for hydrogen because that is a diatomic. Chlorine gas reacting with potassium bromide. In this case, your halogens are similar, so it doesn't always have to be metal for metal or metal for hydrogen. You could also have a reaction between halogens or nonmetals. In this case, chlorine and bromine are switching places. And here's one that looks a little bit more difficult, but the only thing that makes it look more scary is the fact that there's a polyatomic ion in there. But otherwise, you're switching your metals. Aluminum and lead are switching places. Lead isolates itself out, and aluminum bonds to nitrate. However, you do need to check the activity series in order to determine if your single replacement reaction is in fact going to occur. And here is a really nice activity series. Basically, this breaks it up into your most reactive or your most active metals and separates them based on how well they react with different substances. For example, this first group at the top reacts very readily with water. These will react with steam and acids. These do not react with water, so they're broken down that way. We call this an activity series. And your activity series is a list of elements that are organized to the ease with which the elements undergo chemical reactions. Notice at the top, you have your alkali metals and your alkaline earth metals. All of those are really, really reactive. Therefore, towards the top of this activity series, you are going to find your most active metals. These are going to want to replace other metals much more easily than the ones at the bottom. These elements don't like to be by themselves. Their ionization energy is too low. So therefore, they want to lose that one electron to become stable. They're giving that one valence electron away to something else. Your elements at the bottom, so like your coppers, your silvers, your gold, platinum, also your very precious metals. The reason why they're considered precious metals is because they're not very reactive. These are your least active metals. These like to be on their own. They're very stable the way that they are. So when you have a single replacement reaction, your most active metals are going to want to replace the least active metals in solution. So notice here off to the side as well, I do have some halogen nonmetals here. Fluorine, of course, is the most active, being that it is the most electronegative, and iodine is your least active. Sometimes you will need to use this little baby activity series, but for the most part, you'll just be working with metals. Notice hydrogen is down here somewhere towards the bottom. So predicting the products for a single replacement reaction. Of course, you want to identify this single element and the charge that it forms when it's an ion. So you want to find that element that's by itself first. Then you want to determine which element it's going to replace in the compound that's also in that single replacement reaction. So remember, positive replaces positive and negative replaces negative. Check the activity series if the element has the ability to replace. And remember, if the activity of the lone element is lower than the paired element, it is not going to react. However, if your lone element is above the paired element on the activity series, then you will have a reaction. I'm sure you did a single replacement reaction in Chem 1, or you definitely did one in Chem 2. It's the very first lab we do to get you familiar with the lab notebooks. If your lone element is below the element in the solution, it's just going to sit there. Nothing's going to happen. As opposed to if that lone element is more active, it's going to precipitate into the solution because it wants to gain or it wants to lose that extra electron from that polyatomic or that anion, whatever's there. And then you have that other metal that was previously in solution precipitating out. They're kind of neat reactions actually, because you could see metals form on other metals and they precipitate out of the solution. If the reaction is possible, you want to exchange the element with the one it's going to replace. And then of course you want to check for diatomics, and you want to write the formula for the new element, and you want to write the formula for the new compound, and of course you want to balance after that. Next is double replacement, and this is of course a single replacement reaction, but you're replacing 2 times. So ions of 2 compounds exchange places and you form 2 new compounds. General equation, AX plus BY gives you AY plus BX. In this case, we are switching anion for anion. So X and Y are changing places because they are both negative. And you are forming 2 new compounds. So AY plus BX. Remember, you have to switch negative for negative. I can't combine X and Y because they are both negatively charged. You always have to have a positive and a negative. For example, a precipitation reaction, a type of double replacement. So potassium iodide reacts with lead 2 nitrate, and you produce lead 2 iodide and potassium nitrate dissolved in the water. Here, notice we did switch lead for potassium, and therefore I formed lead iodide and potassium nitrate. Make sure you switch your charges correctly though. Here's another one, iron 2 sulfide reacts with hydrochloric acid, and you form hydrogen sulfide and iron 2 chloride. Here your ion and hydrogen switch places. And here's another type of double replacement. More specifically, this is an acid-base reaction or a neutralization. So you have that transfer of a proton here to form water. Hydrochloric acid reacts with sodium hydroxide to produce sodium chloride and water. Here, hydrogen and sodium switch places. Steps to predict the products. So of course you're going to replace cation for cation or anion for anion. It really doesn't matter. The order of the products also doesn't matter as long as both of those products are listed there correctly. Write the new compounds as products. Do not bring over subscripts unless a polyatomic ion is involved. Next, check the states for new compounds using the general solubility rules. If a solid, liquid, or gas is formed, a reaction will occur. So remember, the AP exam only wants you to know the very basic solubility rules. Anything that contains potassium ions, sodium ions, ammonium ions, or nitrate ions will always be aqueous. They are always dissolved in water. Anything else you could assume is a solid. And that's because they're not doing super complex reactions. Just know that potassium, sodium, ammonium, and nitrate, always aqueous. Check the charges, write the correct formulas, and then of course we balance just like always. So here's that really pretty precipitation reaction that you've seen 100 times already. This is a very common one to do in chemistry. So when you have those 2 solutions, potassium iodide and lead 2 nitrate, one of your products is that solid lead 2 iodide, which is right here. And then you still have your potassium ions and nitrate ions floating around in the solution surrounding that. Lastly is a combustion reaction. Combustion reactions are a reaction of oxygen gas with all types of substances. So some of these you'll see are also classified as synthesis reactions actually. That's where it's kind of, these are very broad categories of reactions. General equations, and notice there's 3 of them here because again, a very broad category. Most of the time, your combustion reactions will look like this. You have some hydrocarbon reacting with oxygen to produce carbon dioxide and water. Those are your 2 products, that's it. Usually the hardest thing with these is balancing that correctly. Incomplete combustion. That's when you have some hydrocarbon again reacting with oxygen. Not only do you produce carbon dioxide and water, but you also produce carbon monoxide and carbon. This is what always allows soot to build up either around your candle. Sometimes you'll see that black soot around the outside or in your chimney. My parents have like a little fireplace. It's not a fireplace. The name is escaping me, but they have a little thing in their house, and it always has soot build up on the inside of it. And that's because it's going through incomplete combustion. There is not enough oxygen getting to those hydrocarbons, and therefore it's producing a lot of excess carbon. Your cars actually can go through incomplete combustion as well. That's why you're not supposed to start your car in a garage, is because when your gasoline combines with the oxygen, not only do you produce carbon dioxide and water, but you also produce a little bit of carbon monoxide as well, and sometimes a little bit of carbon, which again is the soot, which is a lot what you see also in those big trucks when they're driving and they have like those big clouds of black smoke. That's the soot from the carbon. You can also have a general equation that looks like this. So just A, some element, plus oxygen yields A2OX. And X, of course, is dependent on whatever the charge for that metal is. So this is synthesis, but it's also combustion. This is why these are very broad categories, which is why we'll talk about later in the unit, those redox reactions, those acid-base reactions, those precipitation reactions. And there's a lot more than just those, but these are the very basic ones that you would need to know for a general chemistry class. Some examples. So we have propane reacting with oxygen to give us carbon dioxide and water. Again, I think the hardest thing with these is balancing them. Here's an example of an incomplete combustion reaction. I will tell you if it's incomplete. I don't think that the AP exam has you do the incomplete combustion. You just have to know anytime you have a hydrocarbon reacting with oxygen, your products are carbon dioxide and water, always. That's the big thing with combustion reactions, CO2 and H2O. Except if you have this next one. So this is just a general combustion reaction. Carbon reacting with oxygen to produce carbon dioxide. Predicting the products for these, it's very simple because honestly, you just have to determine whether it's complete or incomplete. I give this to you. 99% of the time, it's going to be a complete combustion reaction, which means your products are carbon dioxide and water. If it's incomplete, you do tack on those additional two products. And sometimes if it's just that other general one, you just write the formula when it's combined with oxygen. And then you balance. I'm not doing any specific examples with this only because for most of you, this is the third time that I'm showing you these slides because I just kind of copy and paste everything. So I will give you some practice to work on those. And if you have any questions, let me know, but you should be relatively comfortable with this already. Otherwise, if you have any questions, let me know, and I will see you in the next video. Bye.